Okay, let's look at some examples using our parallelogram adding technique. So here, they're asking us to use the parallelogram rule to find the magnitude of the resultant force. Whoops. For the given information, the magnitude of u equals 10, the magnitude of v equals 20, and theta is 135 degrees. This is the angle between the two vectors. So the longest side, I like to put that on my positive x-axis, open up 135 degrees, and draw a vector u about half the distance of vector v because it is a magnitude of 10 compared to 20. So since both vectors are sharing the same point, that creates this angle, and now we have to use the parallelogram rule. So vector u, we're going to slide that to the right to this terminal point. Vector v, we're going to slide it up u until we get to that terminal point. And this is my parallelogram. And not only are opposite sides equal but parallel, but so are opposite angles. So this too is 135 degrees. So here is a whole list of your properties of parallelograms, and I'm going to go to number 2 right here. Adjacent angles of a parallelogram are supplementary. So that means any two side-by-side next-door angles are supplementary. So 180 minus 135 is 45. So my resultant vector is from the two initial points of u and v to the two terminal points when I redrew for the parallelogram. That's my resultant vector. So now in this picture, this creates two congruent triangles, and you can look at either one, but both of them give you a side angle side relationship to find the missing side opposite the 45-degree angle. So that means it's time for the law of cosine. So law of cosines are used quite a bit when we're adding vectors, looking for a resultant vector. So here, the magnitude of u plus v squared equals 10 squared plus 20 squared minus 2 times 10 times 20 times the cosine of 45 degrees. Now, because we're using 45 degrees, which is one of my special right triangle angles, they're probably going to ask you to write a simplified square root answer. Because we are squaring this, we're going to have to take the square root eventually. So if we crunch the numbers, we have 100 plus 400 minus 400 times the square root of 2 over 2. So adding the 100 into 400 is 500. Dividing the 2 into that 400 gives me minus 200 square root of 2. And then we take the square root of both sides. That's my exact value. However, you probably had this happen because Pearson is famous for this. If I were to type in that answer, you would get a pop-up window that says, although your answer is correct, it's not written in its simplest form. So that means we have to be able to break this down. Well, since 500 and 200 have a factor of 100 in them, we are going to take that out as the GCF, and 100 is a perfect square that we can simplify. The square root of 100 is 10, and we can move that out to the front, and we leave the 5 minus 2 square root of 2 on the inside. This would be my exact value for the magnitude of u plus v. If I want a decimal approximation, I'd just go back to the original, take the square root of 500 minus 200 times the square root of 2, and get this decimal approximation. And I rounded it to 3 decimal places. But just to make sure, you might want to type in this bottom answer here to make sure you're getting the same decimal so you didn't make any simplifying errors. All right, example 6. Two forces of 15 and 22 newtons act on a point in the plane. A newton is a unit of force that equals 0.225 pounds. If the angle between the two forces is 100 degrees, find the magnitude of the resultant vector. So here's the vector P to S, which is 22. Here's P to Q, which is 15. This is 100 degrees between the two vectors. Again, build the parallelogram. Adjacent angles are supplementary, so here at Q and S are 80 degrees. Draw in the diagonal, starting at the two initial points to the opposite corner. That's my resultant vector. But again, it doesn't matter which triangle you look at, it's a side angle side again. We're using the law of cosines. Since I called the resultant vector V, then I put those absolute value bars around it squared equals 15 squared plus 22 squared minus 2 times the 15, the 22, and the cosine of 80 degrees. Now for this particular example, because 80 degrees is not a special right triangle angle, there will not be an exact value that you're looking for. This will be all decimal. So we'll just take the square root of all this and go right to the calculator and enter it. And we get 24.38, so we'll probably go to 2 decimal places. So the magnitude of the resultant vector V is 24.38 newtons. Just use the same units for the vectors that they did in the directions. Example 7 says find the force required to keep a 50-pound wagon from sliding down a ramp inclined at 20 degrees to the horizontal. We're going to assume that there is no friction here, so the wheels will just roll freely here. Okay, so here's my ramp. They gave me all kinds of letters in the diagram. Let's describe the vector forces here. So vector B to F. This is the vector needed to keep the wagon from rolling down the ramp. That's what we're looking for. Now at this point B, and again, you usually go from a contact point with the wheel to measure this all up. There are 2 downward vectors going due south. I mean due south, perpendicular to the horizontal. B to A is my force due to gravity. So my 50-pound wagon, that's my gravity. That's this vector. Then completely perpendicular to the ramp is another vector, BC. This is a force vector due to the ramp. And so that vector BF is the exact same vector as AC down here. So in essence, what we do is we build a right triangle similar to this right triangle right here. They're all similar, just a different size. This angle right here is also going to be 20 degrees. It's always the same as the ramp. So how do I find vector BF? Well, vector BF and vector AC are equal to each other. So here's what we do. 20 degrees, side opposite, hypotenuse 50. It's a sine ratio. So the sine of 20 degrees equals the magnitude of vector AC, which is equal to the magnitude of vector BF, over 50, multiply the 50 over to the sine of 20 degrees. We go to the calculator. And so if the magnitude of vector AC is 17.1 pounds, so is the vector for BF. That's the vector we need because they are equal to each other. Example 8, a ship leaves port on a bearing of 28 degrees and travels 8.2 miles. Okay, so here's the port. Bearing, we got to go north and south, east and west. Bearing goes north, 28 degrees in a clockwise direction for 8.2 miles. The ship then turns due east. Okay, so at that tip of that vector, west, east, north, south. Oh, look, west and north intersected. That's going to be a right angle right there. So we have a right triangle here we may need right there. We're going to go due east for 4.3 miles. So since this angle here was 28 degrees in my right triangle, this angle up here in this corner has to be 62 degrees. These two are complementary angles. Well, if this is 62 degree angles, then the angle here forming this sum of those two vectors, they will be supplementary, so that would be 118 degrees. How far is the ship from the port? That's this resultant vector right here. And we have to find its bearing. Okay, well, let's take a look. The distance that we're trying to find is unknown, but we know the angle opposite of it. And you have a side, angle, side. So we have a law of cosines that we can use. So how far is the ship? We'll call that side C. My bearing theta is going to be from the north line to the red vector right here. That will be 28 degrees plus this theta prime right here between the blue and the red vector. So let me throw in a theta prime there. So here's the plan of attack. We'll do the law of cosines to find C. And then we'll use the law of sines to find theta prime. And once we have theta prime, we can add that to 28. And then we'll have our bearing angle, and we'll have our distance the ship is away from port. So let's take care of finding C, side angle side, law of cosines. C squared equals 8.2 squared plus 4.3 squared minus 2 times 8.2 times 4.3 times cosine of 118 degrees. Then we'll take the square root of all that, and you know me, start to get those ugly decimals. I would rather just store them into my calculator. So the square root of a squared plus b squared minus 2ab times the cosine of 118. Store that for C, we get 10.9. So we are approximately 10.9 miles away from port. Then I said we'll use the law of sines. So we'll go the sine of theta prime over 4.3 is equal to the sine of 118 degrees over the 10.9. Now again, if you prefer to put the sine functions in the denominator and the side lengths on the top, that's fine too, but we're still going to cross multiply the 2, divide by the third, and then let's just take the inverse sine of this whole entire statement, and that's what we type into our calculator. So 4.3 times the sine of 118 degrees divided by 10.9. That's what sine of theta prime is. Then take the inverse sine of this. So to the calculator I go. So again, you can either type in the numbers or you can use the letters that you stored and saved. And you can see there is somewhat of a difference when you get to the third decimal place. If we're only going to, let's say it didn't tell us where to round, so my angle, I'm going to say to the 1 decimal place, we'll call it 20.4. Add that to 28 degrees. So my bearing is 48.4 degrees. That's this green arced angle right here, going from the north line and going 48.4 degrees. You can either say to the east or just give the angle measure, because that's always starting at north and then you go in a clockwise direction, but those can go past 180 degrees. All right, example 9, an airplane that is following a bearing of 239 degrees at an airspeed of 425 miles per hour encounters a wind blowing at 36 miles per hour from a direction of 115 degrees. Wow. Find the resulting bearing and ground speed of the plane. Okay, well, based on this angle here, starting north, 180 is south, 239. So we're kind of going in a leftward direction for my flight. So I'm going to put my north, south, west, east line up here. Then rotate 239 degrees, which is about 59 degrees towards the west from the south here. And there's my vector with 425 miles per hour, which means if I fly for 1 hour, it has a distance of 425. Now, as we're flying, it encounters a wind blowing from a direction of 115 degrees. So north, south, west, and east. I extended this just in case I need to make my right triangle here. This will be, let's see, complement to 59 degrees, 31 degrees. 115 degrees, so let's see, that's 90 to the east line. Let's see, 115 minus 90 is 25 degrees, so I'm going to go another 25 degrees. Now, here is the wind. Now, notice the way I drew the vector. The wind is coming from the direction of 115 degrees. So the wind is actually blowing this way. So what's going to happen as my plane is flying in this direction and starts to hit the wind, it's going to adjust the direction and give us a new vector. So I'll draw that vector of 36 miles per hour next to this vector. This angle 25 goes right here. That's the same angle. Those are vertical angles. And now let's see the angle. Let's see, that's my 36. We can find our resultant vector, and we can also find this angle that the two vectors make up. Since you have a straight line, 180 minus 25 minus 31, that's a 124 degree angle right there. By finding that angle between those two vectors, you have a side angle side relationship with, again, we use the law of cosines. I'll call the red vector here my resultant vector c. So I'm going to go c squared equals a squared plus b squared minus 2ab times the cosine of c, which is the 124. Now, we also have to find the bearing. The ground speed is going to be the magnitude of c. The bearing is that original 239 degrees, and then we're going to get another theta prime in there, that little sliver of an angle. We're going to have to add that to it. So our theta will be 239 plus theta prime. So again, just like the last problem, we're going to find the opposite side, which of our 124 angle, find the resultant vector, then we can use our law of sines to find our theta prime. So c squared is equal to 36 squared plus 425 squared minus 2 times 36 times 425 times the cosine of 124 degrees. Yes, we're going to take the square root of that. And again, because the sides are so big, I'm storing 36 in for A, 425 in for B, and plugging it in as the square root of a squared plus b squared minus 2ab cosine of 124 degrees. And I'm going to store that for c in case I need to use c later. I get an answer of 446.130. So we'll round it to 2 decimal places. That's my approximate miles per hour for c. The wind is actually making us fly faster, but it is pushing us off course. To find our new bearing, we got to find theta prime. So sine of theta prime over 36 equals the sine of 124 over our new c value of 446.13. So we cross multiply 36 times the sine of 124 degrees divided by the 446.13. We'll take the inverse sine of that statement and we'll go to our calculator. So again, I use the numbers and I use the stored variables just to show you the difference here. This one's a little bit better in terms of quality because if you notice, we don't get a difference until after 5 decimal points. So theta prime, we'll just call it approximately 3.8 degrees. Like we said, we'll add it to 239. So my new bearing for my plane with the wind in effect is 242.8 degrees.